Hello, everyone, and welcome to Rehab Podcast Weekly. Today, we're diving into the basics. Lever system in human.
Ever wonder why, some movements feel almost effortless, while others feel like a real struggle?
Yeah, it's fascinating.
Today, we're digging into the levers hidden right inside your body. We're talking about how your bones and muscles team up, acting like simple machines to make you move.
Exactly. And we've gathered some really great material for this stuff from CrossFit, the Visible Body blog, a study by M. Porch back in 2002, Study Smarter, PhDN Online, Sports Ed TV, even BioNinja.
Quite the list.
It is. And our mission really is to understand the mechanics behind, well, everything you do, from just getting out of bed to, peak athletic performance.
So we're aiming to reveal how surprisingly efficient our bodies can be, and maybe where their limits are, too.
Precisely. You might see your own anatomy a bit differently after this.
Okay, so let's jump right in. Basics first. When we say levers in the body, what exactly are we picturing?
Well, think simple. A lever is basically just a rigid bar or rod that pivots around a fixed point.
A fixed point, like a hinge.
Exactly, like a hinge. We call that point the fulcrum. Think of a seesaw, the pivot in the middle. That's the fulcrum.
Okay, so in the body, the bones are the rods.
Usually, yes. Bones are the rigid parts.
Got it. And what makes these levers, work? What are the essential bits?
You need three main things. First, there's the effort. That's the force being applied, usually by a muscle contracting, pulling on the bone.
Right, a muscle power.
Then you have the load. That's the resistance, whatever you're trying to move. Could be the weight of your arm itself, or maybe a dumbbell you're holding.
Okay, effort, load, and the pivot point.
And the fulcrum, yeah. The pivot point, which is almost always a joint in the body.
So effort, load, fulcrum. But it's not just where they are, it's also how far apart they are, isn't it? That seems important.
Oh, absolutely critical. We talk about two key distances. There's the effort arm. That's the distance from the fulcrum to where the muscle applies its force, the effort.
Fulcrum to effort point.
And then the load arm, that's the distance from the fulcrum out to the load you're moving.
Fulcrum to load point. And these distances matter because?
Because their relationship, the ratio between them, determines how the lever behaves. It tells you about something called mechanical advantage.
Ah, mechanical advantage. That sounds like getting more bang for your buck, so to speak.
Sometimes, yes. Mechanical advantage is just the length of the effort arm divided by the length of the load arm. Simple ratio.
Okay.
If that ratio is greater than 1, meaning the effort arm is longer than the load arm, you get a force advantage. You can move a heavier load with less muscle effort.
Makes sense. More leverage.
Right. If the ratio is less than 1, the effort arm is shorter, you don't get a force advantage. In fact, it's a disadvantage. But you gain speed and range of motion at the end of the lever.
Interesting trade-off. Speed for force.
Exactly. And if the ratio is exactly 1, well, then it mainly just changes the direction of the force, like that seesaw again.
All right, I think I've got the basics down. Effort, load, fulcrum, and the arms between them dictate the advantage. So let's talk types. You mentioned different classes of levers, starting with first class.
Yes, first-class levers. The defining feature here is that the fulcrum sits between the effort and the load. EFL, you could say.
Effort, fulcrum, load, like the seesaw.
Perfect example. So where do we see that arrangement in us? A great one is right at the top of your neck.
My neck. How so?
Think about your skull balancing on the very top vertebra, the atlas bone. The joint between them, that's your fulcrum.
Okay, the joint is the pivot. What's the effort and load when I say nod?
Good question. The load is the weight of your head, mostly the front part, your face when you nod forward, or the back when you tilt back. The effort comes from your neck muscles.
Ah, the muscles pulling on the skull.
Right. Muscles at the back of your neck pull to tilt your head back. Muscles at the front pull to nod it forward.
So if they pull equally, my head stays level. Equilibrium.
Exactly. And if the front muscles pull harder, you nod forward. Back muscles pull harder, you tilt back. Simple balance beam, really.
Cool. Any other first-class examples?
Yeah, the ankle and foot can act like one, specifically when your foot is off the ground.
Off the ground. Okay.
The ankle joint is the fulcrum. Your foot is the lever arm. The load could be the weight of your forefoot or your heel, depending on the movement.
And the effort.
Comes from muscles on either side. Your big calf muscles, like the gastrocnemius, pull up on the heel via the Achilles tendon. That's effort on one side.
Okay, pulling the heel up.
And then the muscle on the front of your shin, the tibialis anterior, pulls the top of your foot upwards. That's effort on the other side.
So again, it's a balancing act around the ankle joint.
Pretty much. It shows how these first-class levers can manage balance and change direction. We could also mention neck extension again, like looking up.
Right. You mentioned the occipital joint.
Yeah, in that specific motion, tilting way back, the front of the skull is more the load, and the neck extensors pulling on the back have a bit more leverage, a slightly longer effort arm for that action.
Interesting how the same joint can function slightly differently depending on the exact movement. And these body examples, the parallels and tools we use, right?
Oh, definitely. Think about scissors. The pivot is the fulcrum in the middle. What you cut is the load, and your hand provides the effort on the handles.
Right. EFL.
Or a crowbar. You put the bendy part, the fulcrum, near the thing you want to lift, the load, and you push down on the long handle, the effort, way at the other end.
Gives you lots of leverage.
Exactly. Even a teeter-totter follows the same principle.
Okay, clear on first class. Let's move to second class levers. What's their setup?
Second class is different. Here, the load sits between the fulcrum and the effort. So, FLE.
Fulcrum, load, effort. Can you give a real-world example first this time?
Sure. A wheelbarrow is the classic one. The wheel at the front is the fulcrum.
Okay, pivot point.
The stuff you put in the middle, the heavy part, that's the load.
Right.
And you lift up on the handles at the very back. That's where you apply the effort.
FLE.
Got it.
And what does this arrangement do for mechanical advantage?
Ah, this is key. Second-class levers always give you a mechanical advantage greater than one. Always.
Always. Why is that?
Because the effort is always further away from the fulcrum than the load is. Your effort arm is always longer than your load arm in this setup.
Longer effort arm means more force output for your input, a force multiplier.
Exactly. It lets you lift heavy things more easily.
So where's our built-in wheelbarrow? Where do we use this in the body?
The absolute prime example is doing a calf raise. Standing up on your tiptoes. Plantar flexion, technically.
Okay, going up on my toes. What's what here?
The fulcrum is the ball of your foot, those joints where your toes meet your foot, the metatarsophalangeal joints.
Right, the pivot point on the floor.
The load is your entire body weight pressing down through your leg bones, essentially acting through your ankle area, which is between the ball of your foot and your heel.
Okay, load in the middle.
And the effort. That comes from your powerful calf muscles, the gastrocnemius and soleus, pulling up on your heel bone via the Achilles tendon. Your heel is at the back end.
Ah, I see it. Fulcrum, ball of foot, load body weight through ankle. Effort, calf pulling on heel, FLE.
Precisely. The distance from the ball of your foot to your heel, where the effort is applied, is longer than the distance from the ball of your foot to where your body weight effectively acts.
So that longer effort arm gives the calf muscles that mechanical advantage.
Yes. That's why lifting your whole body weight in a calf raise feels, well, possible. It's generally easier than, say, trying to curl the same amount of weight with your biceps, assuming equal muscle strength, of course.
Because the bicep curl doesn't have that second-class advantage.
Right. The calf raise leverages physics in your favor, like the wheelbarrow making it easier to move bricks.
Okay, makes perfect sense. Now, the third type, third-class levers. What's their story?
Third-class levers flip it again. This time, the effort is applied between the fulcrum and the load, FEL.
Fulcrum, effort, load. Example.
Think about using tweezers. The connected end is the fulcrum. You squeeze in the middle, that's the effort. And the tips grabbing something at the far end, that's the load.
Okay, FEL tweezers. Got it. What about the mechanical advantage here?
Well, this is where it gets interesting. Third-class levers always have mechanical advantage of less than one.
Less than one, so
Yeah.
a disadvantage.
In terms of force, yes. The effort arm from fulcrum to where you squeeze is always shorter than the load arm from fulcrum to the tips.
So you have to apply more force with your fingers than the resistance the tweezers are gripping.
Exactly. You put in more effort than the load you're moving.
That seems inefficient. Why would our bodies use a system like that? Especially if it's common.
Because here's the punchline. Most joints in the human body operate as third-class levers. The vast majority.
Wow, really? Most of them? That feels backward somehow. Why?
It's that trade-off again. You lose force advantage, but you gain big time in speed and range of motion.
Speed and range. Okay, give me a body example.
The bicep curl we just mentioned is perfect. Elbow flexion. Your elbow joint is the fulcrum.
Okay, the pivot.
Your biceps muscle attaches to your forearm bone, the radius, pretty close to the elbow. That's where the effort is applied.
Right, muscle pulls near the joint.
And the load. That's whatever is in your hand, a weight, a grocery bag way down at the end of your forearm, much further from the elbow.
So fulcrum, elbow, effort, biceps attachment, load, hand, FEL. Short effort arm, long load arm.
Precisely. That short effort arm means your biceps has to generate a lot more force than the weight you're actually lifting.
Seems tough on the muscle.
It is, relatively speaking. But look what you get in return. A small contraction of the biceps, pulling just a short distance near the elbow,
Yeah.
translates into a much larger, faster movement of your hand through space. Think about quickly reaching out to grab something or throwing a ball. That speed and range is invaluable.
Ah, okay. So it sacrifices force efficiency for movement efficiency, speed, and distance.
You got it. Our bodies often seem optimized for speed and dexterity over raw power in many movements.
That makes sense for things like throwing, reaching, swinging.
Yeah.
What other joints are mainly third class?
Well, your shoulder joint works this way for many movements. Your knee joint when you kick, your hip joint when you swing your leg forward.
So kicking a ball the hip is the fulcrum. The hip flexor muscles apply effort near the hip, and the foot, the load, travels through a big, fast arc.
Exactly. Same idea when swinging your arm from the shoulder.
And are there tool examples for third class beyond tweezers?
Sure, like the inside handle to open a car door. The hinge is the fulcrum. You pull the handle in the middle, effort, and the latch mechanism moves at the other end, load.
Okay.
Or even basic fingernail clippers. Pivot at one end, fulcrum. You press in the middle, effort, and the cutting happens at the other end, load.
Right. Okay, I think I have a handle on the three classes now.
Right.
First class, EFL, is versatile. Second class, FLE, gives force. Third class, FEL, gives speed range.
That's a great summary.
Let's just quickly revisit mechanical advantage, MA, to tie it all together.
Okay, so MA is effort arm divided by load arm.
Right.
First class.
Yeah.
MA can be 1, 1, or 1. Depends where the fulcrum sits.
Hmm.
It can balance, boost force, or boost speed.
Very adaptable.
Second class. Load's in the middle, so effort arm is always longer. MA is always 1, always a force advantage. Think calf raise.
Power movers.
Third class. Effort's in the middle, so effort arm is always shorter. MA is always 1. Always a speed and range advantage, but force disadvantage. Think bicep curl and most other limb movements.
And that really drives home why the calf raise feels mechanically easier than the bicep curl for the same weight. Strength aside, the leverage type is just fundamentally different.
Couldn't have said it better myself. It's all about where the effort, load, and fulcrum line up.
So stepping back a bit, how do the muscles actually do the work with these bone levers?
Well, muscles generate force only by pulling. They contract, they get shorter.
They don't push.
No, they pull. They're attached to bones via tendons, usually across a joint. So when a muscle contracts, it pulls on the bone it's attached to,
Which acts as the lever.
causing it to rotate around the joint, the fulcrum. That's how we get movement.
And we often have muscles working in pairs, right? Like one bends the joint, the other straightens it.
Exactly. We call them antagonistic pairs. The
Yeah.
biceps bends your elbow. It's a flexor. The triceps on the back of your arm straightens it. It's an extensor.
So they work against each other in a controlled way.
Precisely. One contracts while the other relaxes, allowing smooth movement. If both contracted hard at the same time, your arm would just lock up.
It's amazing, even just standing still, there's a constant balancing act, isn't there? Subtle contractions keeping us upright. Muscle tone.
Yeah, absolutely. That baseline tension, that muscle tone, is crucial for posture and stability. It's constant adjustments by these antagonistic pairs.
We keep coming back to this idea that third-class levers, the most common type, are inefficient for force, but great for speed and range. Why this prevalence? Is it just that speed is usually more useful?
It really seems that way for how we interact with the world. Think about human evolution, perhaps. Being able to react quickly, reach for things, throw projectiles, run fast. These actions favor speed and range of motion.
Over, say, being able to slowly lift enormous weights with every limb.
Exactly. While strength is important, the ability to move limbs quickly through a large arc seems to have been a more critical adaptation for survival and function. It's a design choice, favoring agility.
So that bicep curl example, again, the muscle contracts maybe a few inches.
Right, one source mentioned maybe 90 millimeters, or around 3.5 inches.
Okay, tiny contraction, relatively speaking.
But because of that third-class lever setup, your hand might sweep through an arc of, say, 60 centimeters, which is nearly 2 feet.
Wow, that's a huge amplification of movement distance.
It is. It's leverage working for speed and range, not force.
Incredible. Now, we've focused heavily on levers. Are there any other simple machine concepts hiding in our bodies? Briefly.
Yeah, levers are dominant, but not the only game in town. You could think of, say, shoulder rotation as a kind of wheel and axle.
How so?
Your upper arm bone, the humerus, rotates like an axle. Your forearm and hand swing around like the wheel attached to it. A small rotation at the shoulder creates a big, fast movement out at the hand.
Okay. Another speed amplification system. What about pulleys?
Yes, a fantastic example is your kneecap, the patella. It acts like a fixed pulley.
A pulley? For what?
For the tendon of your quadriceps muscles, the big muscles on the front of your thigh, the tendon runs over the patella before attaching to your shin bone.
And what does that pulley action achieve?
It changes the angle of pull. It doesn't increase the force your quad generates, but by changing the angle slightly, it makes the pull on your shin bone more effective for straightening your leg for knee extension. It improves the leverage in a way.
So it redirects the force for a better result. Clever.
It really is. It's not like a movable pulley that gives you a force advantage, but it's a crucial anatomical feature for efficient movement.
Okay, so our bodies use levers mostly, but also wheel and axle and pulley principles too. Just amazing engineering.
It truly is complex and elegant when you start looking closely.
Well, this has been incredibly illuminating.
Yeah.
Let's try and summarize the big takeaways from this deep dive.
Okay. So we've seen the body uses all three lever classes. First class, like the skull and the neck, for balance and changing force direction. Second class, like the calf raise, are our force multipliers. Load in the middle, always giving mechanical advantage 1.
Makes heavy lifting easier.
And third class, the most common type, like the bicep curl or most limb movements. Effort in the middle, mechanical advantage 1. They sacrifice force for big gains in speed and range of motion.
Which turns out to be super useful for most of what we do.
Absolutely. It's a system largely optimized for agility and quick, large movements, even if it means our muscles sometimes have to work harder from a pure force perspective.
It really gives you a new appreciation for everyday movements, doesn't it? And for athletic performance, too. Understanding the mechanics, the efficiencies, and even the built-in limitations.
Definitely. And it leads to a final thought maybe for you listening. How might understanding these lever systems change how you think about things?
Like exercise, maybe?
Yeah, or even just using tools. Could we train smarter or design things better if we work with our body's natural leverage systems rather than fighting against them?
That's interesting. Maybe you'll start seeing these levers everywhere now.
Perhaps. Every time you reach, lift, or walk, it's all physics in motion. Levers hard at work.
Edited by Rehab. Thank you all for listening, and see you in the next podcast.